Hello, everybody. Thank you for sticking around for this short break. And is it worth it? You have chosen the right session if you want to geek out, if you want to deep dive. This session is near and dear to my heart. I meet up with the person presenting every now and then, close to our homes. We don't live that far apart, but I can honestly say that that location is beautiful. But the charts he makes, I guess you spend even more time doing tests with our products than I do. You've probably done more testing than anybody. So without further ado, I would like to introduce Hilko Lantinga from VMware. And I'm just going to keep it short because you just have so many slides. Enjoy.
True. Can you hear me, Mark?
Yes, excellent.
Perfect. Okay, so as Mark said, I'm a bit tight on time, but we're going to talk about how to up your game with these EUC insights, but also about how you can use the Login Enterprise product to get there. Now, for the agenda, I've got 5 items. First, we're going to talk about the Login Enterprise Automation Toolkit. Then I'm going to talk about CPU performance in general, and then also specifically for AMD EPYC. Then we might do something on Retbleed, probably not. Then I'm going to talk about GPU and redirection. And if we have time left, I want to say a few things about the display protocol. So if you have any kind of questions, please post them. I'm not sure if you've got enough time to answer them now, but I might be able to get back to them later and Mark can send them to me. Okay, so without further ado, what is the automation toolkit? Well, the automation toolkit automates the whole process for Login Enterprise, including the generation of pools and kicking off tests. And what you're seeing right here is the way that it currently works. It's with JSON files. So on the left, I've got like a test file. And then on the right, I've got my test runs. And the nice thing about the test runs is that you can actually override settings that are coming from the other files. And as you can see, it's an array, so I can schedule multiple tests after each other. And that's what I did to generate basically everything on this slide. So for me, this is like a game changer, because earlier with Login VSI, what I had to do is I had to come back like every hour and kick off a new test or do something else. And yeah, we could automate it, but it wasn't as great as this is. The other nice thing about the automation toolkit is the report that you get back. And one of the things the report is giving you back is the configuration. So within VMware, we've got multiple teams that are doing testing with Login VSI. And then they send me their report. I look at it and I have like 20 questions first. Like, okay, what kind of host are you running this on? What kind of CPU? Do you have the latest firmware installed? What are the power settings? Things like that. Now, with the automation toolkit and the report you get back, all of those questions are answered. So there's a table in the beginning called configuration. It will tell you everything about the host and about the VM. And it will also tell you something about the software configuration inside the golden image. So which patches were installed, but even more important, was Windows Defender running, was Windows Update running, etc. So we're quite close together with the Login VSI guys, or Login Enterprise guys, not sure what to call them by now. And one of the other things I really wanted is to get better metrics back from vSphere into the report. So what we have here, and we'll get into the details what these actually mean later. But what we have here, we've got a CPU usage graph, which actually gives all of the parameters that matter. Where we've got things on the latency, of the data store. We've got things on the network. We've got the amount of disk I/O. We've got the amount of memory sharing, etc. So what can you get from there? Well, probably for most of the customers here, it's going to be very important that you get your own environment. But for me, it's very simple to do comparisons, like what's the difference between certain configurations. So that's what I did here. Now, the CPU that I'm using for my front end is the AMD EPYC 7543. And doesn't matter if it's Intel or AMD, but one of the most important things to get your performance consistent is the power management of the CPU. So there's 2 types of power management. You've got P states and C states. And the P states are the performance states, so everything that you get above base frequency. And the C states are the level below the base frequency. So you can call those energy efficient states, and the P states you could call power states. Now with the active policy, what you do is you determine how ESXi will do the power management. Now, if you set it on high performance, it will keep all cores active, and that means that you're hitting the all-core turbo frequency if you've got P states available. If you put it at balanced, it's actually turning cores off, and that means that you get higher turbo bins when you've got low load. You get until you reach the all-core turbo speed. And when you do low power, it tries to be a little bit more preservative with the change of the frequency. Okay. Now, why does this matter? Well, because the turbo nowadays can make a huge difference. And it's not just the turbo that matters. The other thing I got here in the diagram is SMT, or simultaneous multithreading, which some of us might know as hyperthreading, which is Intel specific. And with that, every core is presented as two cores, allowing concurrent scheduling. Now, if the resources for one aren't available, like for example, one is waiting on memory, the other one can continue. There still is only one core, but that core is kept busier. Now, the turbo are the P states above the nominal frequency. And while the all-core turbo here is around 25%, the density that you can see in the left diagram didn't rise to 125%. So one thing to keep in mind is that whenever ESXi is doing any kind of sharing, it's determining the amount of time slots that you get. And what happened here is, that's what you can see on the right side, is that some of the extra performance is going into the performance of the individual VMs. So if you add frequency, you get a bit more density, but each individual VM also gets quicker. The same thing for hyperthreading. Okay. Now, I said before that we will have a look at the diagrams a bit later. And I think before we go into comparisons, it's important to understand what we're actually looking at. So when you're looking at summaries in vSphere, you see the usage of a CPU. Now, the usage shown is how close the CPU is to using all the actual cores at the nominal frequency, or the base frequency. Now, under monitoring, there's also an advanced view, and that allows you to see core utilization. And core utilization is how close the CPU is to actually using all cores at the actual frequency, so the turbo frequency. And there you can also find utilization. And utilization also looks at the SMT cores. Now, another very important metric is latency, and this is how often something has to wait to be scheduled. Now, a small percentage is like a crowded motorway. I mean, your average speed drops a bit, but when you hit like your total traffic time doesn't really matter that much. Well, when the motorway is at max capacity and more cars want to join, it's like a traffic jam. And we'll get to why that is later. But in the graph above, you can clearly see that the latency slowly increases to 10%, but then after that, it just jumps up exponentially. Now, when looking at metrics, it's also important to know that vSphere, on the right, uses 20-second intervals to keep the amount of data within reason. Now, ESX stop on a host, which is on the left, has the possibility to go down to an interval of 2 seconds. And an actual cycle of CPU takes a couple dozen nanoseconds. Now, if you extrapolate the difference between vSphere and ESX stop, you can see how a real chart would look like. It would be like a barcode, basically only showing thicker and smaller lines of 100% usage. Now, the percentage shown in vSphere is the amount of time the CPU spends at 100%. In reality, the only thing that exists is 100% and 0%. But it's a matter of time intervals. Now, the other thing to keep in mind is that ESX stop doesn't show the actual frequency above 100%. It does show the actual frequency above 100%. So you're seeing the turbo, but in vSphere, you only get the nominal frequency, or your base frequency. Now, the workload that I'm showing here is like a normal VDI session. The first spikes are the CPU usage from the logon, and then the later spikes are starting Outlook and reading emails. While the average CPU usage is only 30%, if this VM would only have 30% of the CPU power all the time, the logon and the start of Outlook would take like 3 times as long, which wouldn't be a good user experience. Now, with VDI, what you can do is flatten the curve a bit and let different VMs spike at different times. And the important thing here is that you need that headroom. You need to be able to spike. as we will, as I might show in a graph later on, if it can't burst, you can get down to VMs that only have 800 megahertz, meaning your whole VM is performing as an 800 megahertz VM. While if they on average get 800 megahertz, but they've got some room to spike when needed, it's still behaving just as a 3 gigahertz VM. Now, important to notice is that desktop usage isn't like server usage, which is much more consistent, and desktop workloads are very, very bursty. For the interest of time, I'll skip this one. I did that one the last time. Now, the VM has CPU metrics as well. The demand and the usage are very interesting metrics, and I've showed them before when talking about the impact of Turbo and SMT. But the average usage is something you can compare to, use to compare workloads. Now, if the workload above is our lightest workload, an average around 700 megahertz, we can call that 100%, and then compare this with the other workloads and adjust the shares of our CPU time accordingly. If another workload averages 800 megahertz, we can give that 114% of the shares. Another thing we can see is if demand is much higher than usage, if that happens, then the VM was under contention. And we know either the VM had too little shares or the whole system is overloaded. Now, when there is contention, the demand isn't equal to what the workload requires. It will demand to execute something multiple times when it doesn't get scheduled. So you can't just go in and look at the demand and then just say, okay, that's the amount of power that I need. But as long as the demand and the entitlement, the demand and the usage are really close, you know the amount of megahertz that a certain workload is using. Okay, so what we always recommend is to use the VMware OS optimization tool. Now, why do we recommend this? Here you see a chart of a non-optimized Windows 10 21H1 VM. And you can see that at the beginning, we have like the logon process. And then later on, we get either delayed services or scheduled tasks that execute on the system. And they can get quite high, as you can see in this chart, and they can take quite a bit of time. And in between, you would see what we would call like the steady state where it's not doing anything. Now, here's how an optimized Windows 10 VM looks like. And what you can see is that the spike still goes just as high, but it's way shorter. And then later on in the process, so when we get to like the delayed started services or scheduled tasks, there's just a lot less to do. And even the steady state in between is lower than we've seen before. Now, what you can see here is that if you have VMs that behave like this, it's going to be much simpler to fit more VMs in between. So your density improves massively. Another question we get asked a lot is, what about the differences between operating systems? And we did this before, I think it was 2 years ago, and I told you that since Windows 18.03, we had like a steady decline, but after that, it got pretty much to the same level. And since 18.09, which is now the latest that we support, it's basically true. So in purple, I did the average number. That's what you can see over here. You can see that even Windows 11 sits exactly at the average of everything else. And it doesn't really matter performance-wise if you're using Windows 10 LTSC, which is 1809, or if you're using Windows 11. They're so close. We're talking about like a 3% deviation. And that totally disappears when you add antivirus and add a slightly heavier workload. Now, the reason why I'm testing this without antivirus is to make sure that it's a fair test. So antivirus can give large differences between test runs or between days. So that's why these tests were done without antivirus. So Windows 11.
Before we go there, Hilko.
Yeah.
I believe you can hear me.
Yeah, I can hear you.
There is a question actually coming in. I can't see who asked it, but it's a good question. What was the VMware Automation Toolkit displayed? So there were two things displayed: the VMware Operating System Optimization Tool and the Login Enterprise Automation Toolkit. And they work together to give you the best performing desktop. And the toolkit collects additional information from VMware systems like vSphere.
Thanks, Mark.
Hilko.
Yeah, you're skipping a bit. What did you say last?
Go for it, Hilko.
Okay, thanks. Trying to forward a slide, but there it goes. Okay, so talking about Windows 11, does that then mean that Windows 11 is just as resource heavy or light as everything else? Well, that depends. So when we just enable VTPM, there's only a slight difference. But if you want to use like the full security stack, it jumps up, and then the difference does get bigger, and then we see like a 10% difference. Okay. Now, one other thing that people tend to say or even ask, sometimes they ask how many vCPUs do I need, or they make a statement and they go, well, we need 2 vCPUs, right? Because Windows 10 and Windows 11 just doesn't work well without multiple vCPUs. And I'm like, well, not exactly. So at any kind of normal density level, the physical core is shared multiple times, and 2 vCPUs are being scheduled the same amount of time as 1 vCPU. Or to say that differently, does it really matter if you get an average of 1 times 800 megahertz or 2 times 400? Now, 1 vCPU is easier to schedule correctly, both for the hypervisor and the guest OS. Everything else also resides in the same L1 and L2 cache, making unneeded cache misses impossible. And not every bit of the workload can be parallelized, making extra vCPUs less than 100% efficient. And it's something called Amdahl's law. Now, while ESXi does have relaxed co-scheduling, meaning that if only 1 vCPU is active, it doesn't have to schedule all of the vCPUs. It does then need to co-stop now and then to not have a time drift. And if that happens often, there's more contention. Now, this doesn't mean 1 vCPU is always better. It depends on your workload burst requirement and availability. Now, if the workload has tasks that well exceed the performance of 1 core, 1 vCPU isn't an option. Something that is quite likely when you're using a CPU with a low frequency. Now, co-stop exaggerates the traffic jam we spoke about earlier into like a chain collision with multiple vCPUs. So, long story short, if you can get away with it, 1 vCPU, and you can see it on the left in the density diagram, is clearly better. And then in the middle, that's the performance per VM, it's also better. So you get a bit of the best from both worlds. If your workload exceeds it, then you're in trouble and you need multiple. Now, the other thing we can see here is that 3 vCPUs in this case clearly performs the worst, and we're about to see why. So when we're talking about AMD EPYC CPUs, basically they are glued together multiple multi-core dies. So in this case, we had the 7543, and we've got 8 4-core CPUs. Now, the thing is that every single 4-core CPU has its own amount of last level cache. And why does that matter? Well, if you need to reach out to remote memory or even local memory, it's a lot longer. It's a lot more CPU cycles, which you see at the bottom right. So you go from 35 CPU cycles to 400 or 800 cycles. So that part really, really matters. Then the other thing is, if you now think about that system running as I've got 2 CPUs and both have 8 4-cores, if I try to schedule 3 vCPUs on there, it's not an exact good fit. So you can very easily match 1, 2, and 4 in 4 cores. But when you do 3, there's always like a leftover. And then if you want to fill that up again, then you're across multiple last level cache domains. Okay. Oh, one more thing to keep in mind here is that Windows desktop operating systems, they only support 2 sockets, and that's something that really matters. So in this, I showed the divisors, and I show a 2x, and the 2x column basically would be the maximum that you could do with the total performance, and we'll get to the why later, on a desktop operating system. Then the other multiples you see on the far right, that's only on the server operating system. Okay, now when we're talking about a CPU, we always look at the amount of cores, we look at the amount of frequency that we're getting. Unfortunately, most people look at the base frequency or the single core turbo. What you really want to know is the all core turbo. But the other thing that hardly anybody looks at is cache. So what I did here is I took one of my vCPUs, I think this was the 64 core, and I just simply disabled some of those dies, getting less cache, and then also less cache per core. And you can see that the difference is around 18% just by doubling the amount of cache. So for desktop workloads, you can really benefit there. So then within vSphere, you've got the option to not only set the number of vCPUs, but also the amount of vCPUs per socket. And why this matters is that then the guest operating system knows about the physical layout, especially on 7U2 when we have a new scheduler. So if you look on the right here, I did 4 cores per socket, which is also equal to what the CPU is. And you see in red that there's only one unified cache of 32 megs. But when I do go to the middle one, I've got 2 cores per socket. It's shown as 232 megs of cache, which is incorrect. But that means that the guest operating system then doesn't know that all 4 cores can work together. So it makes scheduling decisions that are not correct, and you get a performance loss from that. Now, to be able to do this, you need VMware hardware level 19 or higher. If you take an earlier version like I showed here, it shows you the total amount of cache of the whole CPU, which is like 256 megs. And with the 7U2, you get the correct 32. And you can do this by setting the cores per socket. One for time. I'll skip the VM memory as well. Now, in the summary of this, Mark just went, well, let's also do Retbleed. And I was like, well, we don't have it yet. But he said, oh, you've got some time. And even if it doesn't work out, you can always show that even for you and for us, it's hard to do some things. Well, Retbleed, that's one of those examples. So I've actually tried on Rome, I've tried on Broadwell, but I couldn't see a difference. And I also couldn't see any new microcodes being applied. Well, if I check those CPUs in like the metadata, it says that it's vulnerable and it should be getting a new microcode, and it just doesn't happen. I don't get a new microcode, so I have no numbers on Retbleed, or I could show the numbers on Retbleed, but it's incorrect. And I've got fairly good connections with the performance team, but nobody knew there what was going on either. So that's something for a future presentation. Okay. Now, another thing that I get told a lot is you cannot run Windows 10 without a GPU, or you cannot run Windows 11 without a GPU. Or people say your density goes up when you add a GPU. So I decided to do a test. And what you see in here is in the light blue, I've got no GPU. And in the darker blue, I have a GPU. Not all cases support a GPU, so that's why they don't all have that darker blue one next to it, but the ones that do are listed here. And what you can see here is that there's a higher CPU usage when you add a GPU. And that means that your density goes down. Does that mean that it's bad to use a GPU? Well, of course not. It's like if you have anything that benefits from a GPU. So if you're doing high level of video encoding, or you're doing CAD kind of work, or you've got accelerated applications, or you've got lots of animations, then the GPU will make up for this difference. But if you don't, then all you might be getting is a few more frames here and there and a little bit less latency. But if you're a true knowledge worker or a true task worker, and you're just doing a client server application and you're clicking on a button, waiting for a second for the server to respond and to come back with a value, it's not giving you anything. However, the frame buffer of the GPU needs to be filled. Something is putting data in the GPU, and that is the CPU. And that's the whole reason why your density is not going down. For light workloads, it's actually going, why your density is not going up, the density is going down. That means the CPU usage is going up. Okay, so what if we do something more on the system then? What if we've got Zoom? What if we've got Teams? What if we have WebEx? What if we watch video? Well, for all of those items, for most of those items, especially the ones that are on the screen right now, there are collaboration packs or optimization packs. And what they actually do is that they offload the actual video or audio workload onto the client. And then you don't need a GPU to do any kind of rendering or re-encryption, because that whole video is never actually arriving on the agent. Or for some of them, it is arriving, but it's not being rendered. It's just being sent over the line. So that's a very good way to get your CPU usage down without needing a GPU. Then what do you do for video? Well, we've got multiple solutions for video. So we've got HTML5 multimedia redirection. And what this does is whenever it sees a HTML5 media tag, it's actually taking the bits, sending it over the wire to the client, and then the client does an overlay that's nearly invisible. If you move the screen around very, very quickly, you'll see like black bars and things like that, but it just appears to be local. The advantage of doing this is that you get a real fluent experience, because if you think about what a display codec is doing, it's actually grabbing frames, it's then encoding those frames and sending them over the wire. But it's for a video, especially one that has like fluid movement, it's never going to be at the exact same time every single time. So if I have an object moving with a continuous speed over my screen, let's say 24 times per second, it might get frame number 1, it might get frame number 3, 4, 5, and then it might be frame number 7. So it's always going to be a little bit not smooth, unless you throw a ridiculous amount of CPU power at it. And you can do that, definitely, but then you can't share that amount of power. So it's usually a lot better and much more fluent to do something like this. So is this the only way to do it? Well, no. We have another method, and it's called the browser content redirection. And what we do here is that the whole viewport of the browser is actually loaded on an overlay on the client. And the advantage of doing it this way, instead of just doing the video, is that if you take YouTube and it has like a commercial nag or anything like that, it's now also included. Where with the other method, it might actually show you like a black bar. Now, besides that, we've got one more option, and it's called URL content redirection. And what that does is it opens the URL that you hit on your agent, and it forwards it to the client, and it opens it there in a visible browser. That can get a little bit confusing for end users, so I don't particularly like that option, but for some sites it could be the other good one. And you can watch the slides later to see what requirements we have for what. Now we've got 3 minutes left, so I also wanted to say something about the display protocol. And that is that we've got many protocols by now. We've got BLAST H.264, we've got BLAST H.265, we've got a BLAST codec, we still support PC over IP. So what do you choose and what are the differences? And then even between them, we've got various options. So what you see here on the screen, it might be hard to see for you, but you should see it later in the PDF. In the middle, in blue, I've got the native machine, and I just did a screenshot. And if I compare that with my eyes, it's absolutely identical to the BLAST PNG and the BLAST codec. And for PNG, that makes sense, because PNG is a lossless codec. But the BLAST codec isn't lossless, it's lossy. But it's optimized in such a way that it gets to 80% of the quality of a native machine. And our human eyes are not capable, according to testing, to spot the difference. And it's true, I really can't spot the difference. Now, BLAST H.264, on the other hand, I can immediately spot a difference. And then it depends on the settings of BLAST, how big that difference actually is. If you bump up the settings very much, it gets into the same level, but out of the box, it's not as great. On the NVENC version, which is the GPU accelerated one, it's even worse. So you see a bigger difference. Well, BLAST H.264 might have a little bit less quality, but when you have a high frame rate, it does matter. So what I did then is, and this is the only thing that I did do with the workload from Log and VSI, but I used other tools. I used Take-Two Photon tools and things like that. But I did a comparison for myself. So I did all of the codecs, and then I looked at the CPU usage, the image quality, the bandwidth, and the latency, and the FPS. And that's what you see on the left side. And if you look at that, it's like, it all just looks the same. This does this a bit better, that does that a bit better. But when you then check on what matters for your use case, so I thought, well, for a knowledge worker, the quality is more important than the CPU usage. And then the bandwidth is even less important, and then the latency, and then the FPS. And if I order it like that, you see that the BLAST codec gets the clear winner. Now, if we're doing any kind of 3D or CAD, then you can just basically flip that whole chart, because then the FPS matters most. And then you will see that the BLAST H.264 codec will come to the top. If you're doing anything medical and you absolutely need lossless, then yeah, PNG is the most important one. So that's how you make a choice. And Mark, I think I might be able to answer one question if you've got one. Mark, are you still there?